So we then moved from correlation, and again with correlation, what we're looking at is the R, which is the calculated value of the actual equation. And after R, we report the degrees of freedom, which in the case of correlation is n minus 2. We then report the actual calculated value. We look at that calculated value compared to the degrees of freedom on a chart to determine whether that value is large enough for us to claim statistical significance at a p less than 0.05. And if it is, we report that p at least less than 0.05. And then finally, if it's significant, we report its effect size, which is r squared. Then we talked about regression analysis, which simple regression analysis gives us very similar information to a correlation, but it adds a few things. One, it adds eventual variety. We can use regression to look at a lot more complex questions than we can correlation. But at simplest level, the main thing it gives us is the regression equation. So where we run correlation in SPSS, we get our R, we get our P, we get our degrees of freedom, and we can calculate our R squared. We get more information with regression analysis. We get our y-intercept, we get our b-weight, we get our beta, and the beta is tested with a t-test. So our degrees of freedom is still n minus 2, but in this case, we'd actually report both the b-weight, 3.842 in this case, the beta, 0.369, then we'd report the t, 3.249. That's where we'd put the parentheses for our degrees of freedom, n minus 2, and finally we'd report the significance. This is also a good place to remind you that we never report a significance of 0.0. We always report down to 0.001, and if it's lower than 0.001, or if SPSS says the significance is 0.000, we'll simply report less than 0.001. The reason for this is that P is a probability estimate, and the probability of being wrong is never 0. It's always a very, very small number, but it's never 0. That's why we always round to 0.001 when reporting P. Now, the regression equation allows us to use correlations to make predictions in future samples. So we use a single sample. So we have a sample of people that come into our study. We measure the two variables we're interested in, and we run a regression analysis. From that regression analysis, we get whether it's significant or not. We get information about the effect size, but we also get numbers that allow us to do future predictions in a new sample. And in that new sample, those would be people that we only actually have their value on the first variable, what we think is the predictor variable, what we think is the antecedent, what we think is the independent variable. And based on that, we can then use someone's score on that particular variable to predict what their score on the other variable would be without actually collecting that data. And how we do that is we take the b-weight, so again, in this case, 3.842, it's always going to be the under B in the SPSS readout under the actual name of the variable that we're actually interested in. In this case, the variable we're interested in is attendance. And what the b-weight is the amount of change in our DV, in this case test score, for every 1 unit change in that IV. So this basically says test scores go up by 3.8 points for every day of attendance. So if we know someone's attendance is a 10, we would simply times 10 by 3.842. That is the start of our regression equation. Now remember though that most of the time when we're looking at various scales, they're fairly arbitrary as far as what's the lowest and highest value on that scale. That's why we need the intercept, and that's often referred to by lowercase a, and it is the y-intercept, and it's basically what would we predict the person's outcome would be if they didn't attend at all. What if they had a 0 on that x? And not all scales will have a 0. Remember, interval scales often don't. But b-weight, or the y-intercept, the a, is always what if there could be a 0, what would that prediction be? It's the start point of our equation. And what this equation basically tells us is that if you never attended, the lowest score we'd ever predict would be a 62.507. So to calculate someone's predicted score, we start with the lowest score possible according to our prediction, 62.57, and then we add points to it based on their amount of attendance, and that would get our prediction. So again, if we had someone attending 10 days, that's a 38. We'd add 38 to 62, and that would be 100. We'd expect a perfect score at that point. We then talked about Z or standardized scores. And remember, when we were talking about standard deviation gives us information about what a standard deviation unit is on the scale of measurement. In other words, it's not standardized, it's actually tied to the original scale of measurement. So it can vary from scale to scale. A standard deviation of 100 may be smaller than a standard deviation of 0.5, depending on what the original scale was. But what it does tell us is whatever that value is on a standard deviation, that is one standard deviation unit above or below. So again, if I have a mean of 22 with a standard deviation of 4, that tells me that if I have a 26, I'm one standard deviation above the mean of 22. If I have an 18, I'm one standard deviation below the mean of 22. And also with that information, if it's normally distributed, it also gives me a pretty good guess based on standard deviation units where someone's score lies within that variance. We also can use standard deviation scores to get a very good idea of where the variance kind of peters out. Most normal distributions lie between plus or minus 3 standard deviation units. The problem with standard deviation units, I hopefully have already communicated, and that is that they are still tied to the original measurement scale. In other words, you can't compare one standard deviation score from one measurement to a standard deviation score on another measurement unless those scales are exactly identical. What a z-score allows us to do is to actually calculate, based on the standard deviations, a standardized score on standard deviations. So z-scores are always in units of standard deviations of basically 1. So a z-score of 1 is a standard deviation of 1. A z-score of 2 is 2 standard deviations, and it always is the same. No matter what your measurement scale is, z-scores will always generally range between -3, so that's 3 standard deviations below the mean, and +3, 3 standard deviations above the mean. And in order to calculate this, we have to know how to calculate a mean, and we have to know how to calculate a standard deviation. Because the way to calculate a z-score is we take the person's individual score minus the mean of the sample divided by the standard deviation of the sample, and that puts it on a standardized scale where 0 is the mean. 1 is one standard deviation above the mean. And because of this, we can now use z-scores to compare any original measurements of any scales because they're now they're not related to those scales anymore. They're independent of the measurement scales. It's a now standardized scale that simply reflects the standard deviation units away from the mean, plus or minus. And again, just like standard deviation units on any distribution, it falls into the same kind of pattern, assuming we have a normal distribution. A z-score of -1 to +1 is going to be about 68% of the population, and about 95% of the population is going to lie between a -2 and a +2. So if someone has a z-score above 2, you know that 95% or more of the population actually is below that person's score. And if someone has a z-score of -2 or more, you know that 95% of the people who are above actually scored better than that person. So again, this gives us ideas of where did the person's score actually fall in the distribution, regardless of the original measurement scale. So after z-scores, we then moved a little bit on to the z-test for simple samples, and I'll talk about that as well. But as we start to put together this toolkit of various statistical techniques, I really want to take a moment to stop and remind people that the reason that we're looking at this, the reason that we're talking about what kind of variables do you have, what are the predicted relationships between those variables, is so that you can choose the appropriate statistical test. So currently, as far as inferential tests, and those are statistical tests that gives us a probability estimate, they give us a p-value. We have correlation, which is appropriate to use when we have two continuous variables, and we're not interested in a prediction. We have simple regression, which is an appropriate test to use when we're actually interested in looking at not only a relationship between two continuous variables, but we also want to make future predictions from that relationship. And we're about to talk about the z-test for single samples when we're comparing our sample on a particular variable to a known value out in the population. And all of those, correlation, simple regression, and z-score for single samples, are statistical significance tests. They're inferential statistical tests. They're equations that give us an idea of is there a relationship, and then puts a probability factor on how likely that relationship is due to it being a systematic, meaningful relationship and not pure chance. So on all of these inferential statistics, what we're doing is we're comparing the obtained test statistic, so the value we calculate, to a test statistic probability distribution. So we have some definitions here. The obtained test statistic is the test that we actually calculate. It's what we are calculating using the equation. The test statistic probability distribution is a table that indicates the probability of getting any particular value from a test statistic based on the sample size. The critical test statistic is the value on that table that represents our sample size and is the value we need to see our obtained test statistic be higher than for us to claim statistical significance. The p-value is the actual statistical significance value of a particular test, and our alpha level is what is our criteria for accepting a test as statistically significant, and we have set that pretty much as a science at 0.05. So again, when we run a statistical test, we're going to get a value that we calculate. We're going to find out what is the minimum value that value could be for us to claim a significance of 0.05 or less. And if it has met that value, we're going to claim a p of less than 0.05. We're going to claim statistical significance. This doesn't mean that it is a big difference. It doesn't mean it's a meaningful difference. It simply means that it's a difference that we can, relatively speaking, trust. We can basically be 95% confident that it is a real relationship. The question now becomes, is it a meaningful or useful relationship? We also talked a little bit about some statistical tests are going to ask us if we have a one-tailed or two-tailed hypothesis. In other words, basically, do we have a directional hypothesis or an undirectional hypothesis? A directional hypothesis is often referred to as a one-tailed test because at the end of the day, we're comparing our critical test statistic, the value we calculate, to a normal distribution of potential outcomes. And those outcomes can range anywhere from a very low number to a very high number to the most average number. And the average number would be no relationship whatsoever. So a one-tailed test means that we have a directional hypothesis. We expect to see either an increase or a decrease, which means that we can accept any score that falls within that 5% of values, either on one tail or the other of the distribution. So our critical value is set at 95% chance of us rejecting it if we're not sure, and a 5% chance of not rejecting it if we're 5% or more confident that there's not an error. So we reject the null hypothesis and make the claim of statistical significance if we're in that 5 percentile. And if we're not, we reject and claim no relationship. When we go to a two-tailed test, we have to split that 5% up to each tail. So a two-tailed test with an alpha also again of 0.05, now because it's a non-directional hypothesis, we haven't actually stated whether we expect an increase or decrease. We still have to divide up the 95% of values that we would reject and the 5% of values that we'd accept. Except now that 5% has to be split in half, 2.5% on each tail. So the value we would have to actually calculate, whether positive or negative, when we're actually calculating our statistical test, our formula, would have to be higher for us to claim statistical significance with confidence in a two-tailed test. And this is why, when possible, due to either theory, logic, or past research, we generally want one-tailed directional hypotheses and tests. So let's quickly talk about that z-test for single samples. It's a fairly straightforward equation, but there's a component that has to be pre-calculated before we put it in the equation. And the question here is the sample mean significantly different than a population mean? And again, it's a known population mean. And to calculate that, we need to have three pieces of information. We have to have the mean from our group, our sample. We have to have the population's mean and the population standard deviation. If we have all three of these, we can run the z-test for single samples. Now, how we run this is we actually start by calculating the bottom of the equation. And the bottom of the equation is actually the population standard deviation, represented by sigma, divided by the square root of n. That becomes our bottom of our equation. So basically the sigma of our mean. And then the top of our equation is simply our mean of our sample minus the population mean divided by that value we already calculated. And once we have that value, that is our obtained test statistic. That's our equation for this statistical test, this inferential test. The neat thing about this one is we don't actually have to calculate degrees of freedom. It is simply set on whether it's a one-tailed or two-tailed hypothesis. If it's a one-tailed hypothesis, so we're looking at one direction, we need to see a score, a z-score of above 1.645. And the reason this is an obtained z-test is this is in standard deviation units, just like a z-score. This represents that our effect size was 1.645 above the mean of potential test scores you could find if you were looking at them due to just chance. In other words, this score is unlikely to occur randomly, less than 5% of the time. If it was a two-tailed test, it's got to be 1.96 or higher. So again, it's a higher number, it's harder to obtain. So the assumptions of the z-test, we have to know the population's mean, and we have to know the population standard deviation, and we have to have a sample mean using interval or ratio data that we collected. There has to be a normal distribution of that data, and finally, our sample size has to be over 30. So we finally ramped up the last couple of lectures talking about hypotheses, how we create hypotheses, again, testable questions, and basically the hypotheses are held to the same standards of all of the other parts of psychology that we've talked about. Is it a rigorous question? Is it supported by theory? And is it stated in such a way that can be statistically tested? Now, when we're actually looking at our p-value, again, our probability of error, remember that it's a probability. We don't know for sure, but there's basically four possibilities that can occur. We can basically claim there's no effect when in fact there isn't an effect, and that's basically we're correct. We didn't find anything and there was nothing to find. Not very interesting, but at least we're correct. And then finally, then the other alternative is that we claim there's an effect and there is an effect, and that's what we often refer to as power, and that's what we're trying to strive to. And the cards are stacked against us here. We have basically that p of 0.05. We need to be 95% confident or greater before we actually claim that we actually are accepting our alternative hypothesis and that we are claiming an effect. Do recognize there's two types of error that we have to worry about here. The type 1 error is when we claim there's an effect and there isn't. And that's one of the reasons science has set this at a pretty high bar, that we have to be basically 5% or less likely to actually make a type 1 error before we make an effect. But that does mean the type 2 error is probably more likely in general. Because we're rejecting p-values of 0.6, 0.7, and again, a 0.06 means only a 6% chance we're wrong. 0.07 is only a 7% chance we're wrong, but we'd reject those. And at that point, we're making a type 2 error. We're claiming no effect when there actually was one. And we have decided as a field that we would rather miss some occasional effects than erroneously report effects that are not true. And finally, we wrapped up on kind of talking again about the various methods of qualitative data analysis and the difference between qualitative and quantitative data analysis. I would suggest that you actually make sure that you know the differences of the various types of observational qualitative data, that you understand the difference between archival and content analysis in qualitative data, and that you at least have a vague idea of kind of grounded theory approach to looking at qualitative data. But remember that qualitative research is often viewed as confirmatory and deductive in manner. And deductive means that you kind of start at, quantitative. Quantitative research, my apologies. Quantitative is viewed as confirmatory and deductive. Deductive means that you already have a theory, you already have research, you already have questions. You're going to create a methodological system that probably involves numbers to put through an inferential statistical test to be able to make a deductive conclusion. Is your theory supported or not supported? And that's mainly quantitative data. Qualitative research is generally exploratory and inductive. So we start with observations, we try to generalize those observations, and again, the more systematic, the more rigorous this process is, the better, to create a theory. But once we have that theory, we then want to bring it to the test, which we often will do with quantitative. And this is really just a reiteration and a reminder that qualitative and quantitative are not necessarily right or wrong. They're simply two different ways and two different methods, and often it depends on where you're at in the research process. If your research question has been well researched, there's a good chance you're going to want to mainly look at quantitative unless you're trying to branch out in a new direction, when you might be looking at qualitative.